talk about the thermal effect of electric current. Now, what is this thermal effect of electric current? As you all know, as you have experienced, almost all the electric equipments and electric conductors get heated after a certain time of its current flow. You all know when an electric current flows through a conductor, the electrons collide with each other and with the atoms and cations of this conductor. What happens here is the kinetic energy of these electrons get lost because of these collisions. So that obstruction for the electron flow created by these atoms and cations is called this resistance. You all know that. So because of this resistance, the kinetic energy of electrons is lost. This loss of kinetic energy of electrons is converted into heat energy. So always there will be a resistance to the current flow, and hence thermal energy is produced in these cases. So this production of thermal energy due to the resistance is called this thermal effect of electric current. So simply what happens is when electrons flow due to the resistance of the conductor, energy of the electrons lost, and that energy lost is converted to thermal energy. So this is called the thermal effect of electric current. Under this, you have to learn the Joule's law of electrical heating. Joule's law of electrical heating states that the thermal energy, I'll denote it by capital E, thermal energy generated due to the flow of electricity through a resistor is directly proportional to the current flowing through it, to the square of the current flowing it. It also says the thermal energy is directly proportional to the magnitude of the resistance of the resistor. Also it says this thermal energy is directly proportional to the time of current flow. So from this we can build up a relationship. Thermal energy is directly proportional to I squared RT. You can write E equals K, use a proportional to constant, I squared RT, and this K is found to be equal to 1. So finally you get E equals I squared RT. Now this is the equation you should remember. E is equal to I squared RT. This is what you should remember. Now I'll teach you what an ideal resistor is. If the total electrical energy flowing through a resistor is converted to heat energy, means the thermal energy, such a resistor is called an ideal resistor. Here that electrical energy is converted only to heat energy. So these ideal resistors obey Ohm's law. Now we know the expression, the equation we got for the thermal energy generated across a resistor is equal to I squared RT. Now for an ideal resistor we can write, since it obeys Ohm's law, V equals IR. And here we can write this E equals I squared RT as E equals IR, this I squared, one I from this I squared is taken out, IR into IT. Now this IR, instead of IR we can write V here, because V equals IR. It obeys Ohm's law, so we can apply Ohm's law. So E equals V I T. You know V is the potential difference across this resistor. So we can derive another equation like this. Also from this we can derive, we can subject I here. I will be equal to V over R. V over R. So now here, instead of I, we can use V over R. So we can write E equals, since it's I squared, it's V squared over R squared into RT. 1 R to 1 R gets cancelled, so we get V squared over R T equals V squared T over R. This is another equation we can derive from this equation we derived earlier. Now let's talk about electrical power. Electrical power is denoted by capital P. Electrical power is related to electrical energy. Now what is electrical energy? Electrical energy is this energy of the electrons which flow. And what is electrical power? It is the amount of electrical energy which is released per unit time. So this energy released through an ideal resistor is always equal to this thermal energy. If we consider the electrical energy released through an ideal resistor, it is always equal to the thermal energy. The total amount of electrical energy is converted to thermal energy. So the electrical power we speak here is this amount of thermal energy released per unit time. The common equation for electrical power. Power is energy, electrical energy released per unit time, E divided by T. Power is E divided by T. So for these ideal resistors, we can substitute the equations we derived earlier for this E. So then we can write an equation, what you know equals, first you know I squared RT, and you know equals V squared T over R equals VI T. So these are the equations we derived earlier. So you can substitute this instead of E here. So then power can be written as, first is I squared RT over T. T gets cancelled. Power equals I squared R. Also power equals this V squared T over R divided by T. T gets cancelled. Power equals V squared over R. In this equation, power equals VIT divided by T. So from that you get power equals VI. So now you derived 3 equations for electrical power. So when applying for ideal resistors, you can directly use these 3 equations according to the data they have given. Okay, you will remember these 3. Since we learned about this power, I'll teach you now about the voltage of an electrical equipment. So you have seen in these electrical equipments, bulbs, any kind of electrical equipment, a voltage is marked in it. So what is this voltage now? That is the relevant marked potential difference. Voltage is now when the relevant marked potential difference is applied between the terminals of a certain electric equipment, the power at which it works is its voltage. Now before learning voltage, actually you should know about this voltage of an electric equipment. That is this relevant marked potential difference of it. So I'll teach you both here. So what is the voltage of an electric equipment? It is the power at which this electric equipment works when the relevant marked potential difference is applied between the terminals of that electric equipment. So I'll teach you what that marked potential difference or the marked voltage of that electric equipment means. So when that relevant voltage is provided, the power at which this electric equipment works is called the voltage of this electric equipment. So this is what is defined as the voltage of an electric equipment, and I'll write some examples here. That voltage is the units of voltage is watt. So examples will be 5 watt, 10 watt, 100 watt. It's watt. This W is watt. You all know this from all levels. So now I'll teach you about this voltage or the potential difference which should be applied for an electrical equipment. Now what is this? This voltage of an electric equipment is also marked in almost all the electric equipments. That voltage is the value of the potential difference that should be applied between the terminals of that electrical equipment in order to function it safely, in order for it to operate safely. Now I'll denote this by capital V. Now consider an instance where you apply a potential difference greater than this standard voltage of the electrical equipment. What will happen? Consider the potential difference we're going to apply as V dash and this standard voltage of the electrical equipment as capital V. Now if this V dash is greater than capital V, what's going to happen? If the potential difference we apply is greater, the current which flows through the electrical equipment increases. So if the potential difference which is applied between the terminals of this electrical equipment is greater than the standard marked value of it, what happens is here potential difference greater means we provide a greater energy, so a greater current flows through that resistor. So here the current increases, current flowing through the resistor of this electrical equipment. So an electrical equipment has a resistor, so it acts as a resistor here. So the current through this resistor increases. So when the current is very high, there is a high chance for this electrical equipment to get burned. So it will burn. The equipment will burn. Now what will happen if the potential difference we apply, V dash, is less than this standard potential difference, standard voltage of this electrical equipment? In this case, the energy we provide is less. So there's no damage to the circuit here, but only the power at which it works will decrease. So here the current flow through the resistor will not be its maximum current. So the equipment won't burn. No damage to the circuit. But what happens is the power at which it works decreases. It means it won't work with the standard, with the wattage, with the standard wattage of it. Power at which it works decreases. Normally the voltage of this electrical equipment is given by the manufacturer. It depends according to the country, because from country to country the voltage provided by these power stations through electrical wires to houses is different. Now in Sri Lanka the voltage supply for houses is 240 volts. So the electrical equipments made in Sri Lanka are marked with the voltage of 240 volts. It's the standard voltage. But in other countries it varies. So the voltage supply to houses in Sri Lanka is 240 volts. This is the usual value, but in questions you might get different values, 230, 250 maybe. So, but this is the standard value. The other thing, so there's another thing you should know when talking about this electrical equipments. It is fuse. You all have heard these. What are these fuses? Fuses are used to avoid the flow of current greater than the maximum current that can flow through a certain circuit. So if the current exceeds the maximum current that can flow through the circuit, what happens? The temperature of these coils or the resistors increase, and they will reach to the melting point. So the circuits will get damaged. So in order to avoid this, these fuses are used in electrical equipments for its safety. So they are used to avoid the flow of current greater than the maximum current that can flow through a certain circuit. Normally fuses are also resistor wires. So these are thin resistor wires which will get melted, and the circuit will break, and the heavy current flow through the circuit will be prevented. So normally resistor wires are used for fuses. So these fuses are marked with the maximum current which this fuse allows to flow. So there are example, this will be fuses with 5 amperes, means the maximum current that this fuse allows to flow is 5 amperes. 2 amperes, 10 amperes, likewise fuses are there. Now let's talk about the application of principles of energy for simple circuits. Consider a simple circuit like this. If you consider the EMF of the cell as E and the internal resistance of the cell as simple R, and the value of this resistor is capital R, and the current flowing through the circuit as I. Now this is an ideal resistor. Consider this as an ideal resistor. Now what is an ideal resistor? The energy lost from this resistor is converted only to thermal energy. And consider this internal resistor also as an ideal resistor. Now what is this EMF of the cell? E we defined earlier. It is the total electrical energy generated due to the flow of a unit charge through the circuit. When a unit charge flows through the circuit, the total electrical energy generated is this E, EMF of the cell. So now that is the total electrical energy. Now consider this external resistor. The total electrical energy moving through this external resistor is converted into thermal energy, because we consider this as an ideal resistor. So we can write the heat energy, the thermal energy or the heat energy. Heat energy generated from the external resistor equals I squared RT. Current flows through the resistor is I squared R, time which the current flows is T. We derived this earlier, equals I squared RT. And also we can write for this internal resistor, heat energy generated from the internal resistor equals I squared simple RT. So if we consider the total energy flow during a time t, the total electrical energy flowed during a time t is converted to this heat energy generated from the external resistor and the heat energy generated from the internal resistor. Therefore, the total energy flow during the time t equals the sum of these two. So then, according to the definition of EMF, which is the total electrical energy generated due to the flow of a unit charge through the circuit, we can write this total energy flow during time t for a unit charge. So that will be equal to the EMF of the cell. So E equals I squared RT plus I squared simple RT, heat energy generated from the external resistor plus heat energy generated from the internal resistor, divided by the charge which is flown, charge flow. So that will be then the energy generated for a unit charge, which is equal to the total electrical energy supplied by this cell, EMF of the cell. And you all know Q equals IT. So this Q can be written as the amount of current flown for a time t. We have written this total energy flow for a time t. So now instead of Q you can write IT. So E equals I squared RT plus I squared simple RT divided by IT. So then you can get this IT to this side. Then EIT equals I squared RT plus I squared simple RT. So now according to the relationship we obtain, EIT is the chemical energy supplied by the cell, and I squared RT is the heat energy generated by the external resistor, and I squared simple RT is the heat energy generated by internal resistor. So the chemical energy supplied by the cell will be equal to the sum of the heat energy generated from the external resistor and internal resistor of a simple circuit. So if you divide this entire thing by t time, what you will be getting is the power. Power equals energy divided by time. So this divided by t gets cancelled. So power can be written as EI equals I squared R del R plus I squared simple R. So this will be the relationship for the power generated by a simple circuit, and this is for the energy. Also, you can derive that same thing in this way. Now you know for a simple circuit we can write equals IR plus R. This is the equation for a simple circuit. If you multiply this, so you can write it as equals I capital R plus I simple R. If you multiply this equation by capital I, what you're gonna get is EI equals I squared R plus I squared simple R. So what is this? This is the relationship for the power generated in a simple circuit. Power, and when you multiply that equation by the time t, you will get the equation for energy. So you can derive this these relationships by this method as well, but this is the logical method of deriving it. Now let's talk about the efficiency of a cell. Now what is efficiency? So the efficiency of a cell is equal to the useful power divided by the chemical power generated by the cell. Okay, now we wrote the equation for the chemical power generated by the cell earlier. It is equal to EI. Okay. Now what is this useful power released from the cell? Means the power which we can use from a cell. So you know the cell has its internal resistance. So part of the power generated by the cell is used within itself to overcome the internal resistance of the cell. So the power which it gives out will not be the chemical power generated by it. It will be the chemical power generated by the cell minus the power across the internal resistance of the cell. So what is the useful power released actually from a cell will be the power of the cell, which is EI, minus the power across the internal resistance of the cell. So that will be the power given out. It is the useful power. Therefore, the efficiency of a cell, we denote it by eta. So eta will be equal to useful power is E capital I minus I squared R. Power, chemical power generated by the cell is EI. If you cancel I here, eta equals E minus IR over E. Now what is E minus IR for a simple circuit? Now I am writing this efficiency for a simple circuit actually. And so E minus IR for a simple circuit is V. Now consider a simple circuit like this. It has a resistor. So now you know this E minus IR is equal to the potential difference across this external resistor. So what is it? V, if you write it as V is equal to IR. A simple circuit we write equals IR plus capital R plus I simple R. So E minus I simple R equals to I capital R. So instead of this we can write I capital R or V. V over E or IR over E. So this I, now what is I here? From this equation you know equals IR plus R. So I is E divided by capital R plus simple R. So instead of I here, you can write this. Eta equals E over R plus R into R divided by E. So what happens? E to E gets cancelled. So eta equals capital R divided by capital R plus simple R. Now this is an important relationship. You should remember, eta means the efficiency of a cell of a simple circuit is equal to the value of the external resistor divided by the value of the external resistor plus the internal resistor. You should remember this relationship. In this part, you should know about two graphs, that is the variation of the power with the external resistance of a simple circuit and the variation of efficiency of the cell with the external resistance. So first let's see the variation of the power with the external resistance of a simple circuit. Now you should remember this variation. You can draw it like this. Now if you draw a graph with the y-axis for power of the external resistor and the value of the external resistor in the x-axis, the graph that you will be getting is something like this. Okay, here the maximum point of the graph means the maximum power. The maximum power P max is given when the value of the external resistor is equal to the value of the internal resistor. When the external resistance is equal to the internal resistance, the maximum power is obtained. And at the maximum power, we can write the efficiency equals eta equals R. Now you know R over R plus simple R into 100. This is the equation for eta we derived earlier. Okay, so at maximum power what happens is this also equals to simple R, means actually becomes 2R. So this is equal to 50%. So at the maximum power, the efficiency will be 50%. Variation of the efficiency of the cell with the external resistance can be drawn like this. It is like this. So when the efficiency is 50%, the value of the external resistance is equal to the value of the internal resistance, simple R. So this will be when the efficiency is 100%. So this is all what you should know under the thermal effect of electric current in the unit current electricity.
Thanks for watching. Hope this video was helpful. If you did, make sure to give it a thumbs up and leave a comment below. Subscribe us and click the bell icon for more videos like this.